The hour is late. The world outside is quiet. But here, in this laboratory, something is waking up. A lone scientist stands before a colossal, shimmering machine. It looks like a chandelier made of gold and silver descending into a deep, cylindrical chamber. Wires snake away from it in every direction, feeding into racks of blinking electronics that hum with a low, steady energy. The air is cold, chilled to temperatures colder than deep space. This is not a place for ordinary things. It is a place where the rules of reality itself are being carefully bent, manipulated, and put to work, for a purpose that feels almost like science fiction. On a nearby monitor, a single clock is counting down. It's not counting down to a launch or an explosion. It is counting down to a single, monumental calculation. This calculation is a question, a puzzle so complex that every supercomputer on Earth, working together for thousands of years, could not hope to solve it. Yet this strange machine is being asked to find the answer in mere minutes. The scientist watches, her breath held tight. She is not just running an experiment. She is knocking on the door of a new reality, a new era of computation that promises to redefine everything we thought was possible. The heart of this machine is a tiny, glowing chip. It is smaller than a fingernail, yet it holds a power unlike anything we have ever built. This is not a classical computer chip, which works with simple ones and zeros. This is a quantum processor. It operates on the strange and ghostly principles of quantum mechanics. It harnesses the weirdness of the universe at its smallest scales. The particles within it can exist in multiple states at once. They can be mysteriously linked across space. They are dancing to a tune that defies our everyday intuition, a whisper from the very fabric of existence. The clock on the screen hits 0. A stream of data floods the monitor. The machine has finished its work. A single answer appears. Is it correct? Has it worked? This single moment represents a profound question for all of humanity. Can we truly build machines that use the bizarre rules of the quantum world? Can we unlock a power that could solve problems we currently consider impossible? This is not just about faster computers. It is about a fundamental shift in our ability to understand and shape the world around us, from medicine to materials, from finance to the very nature of intelligence itself. The world of quantum physics can feel distant and strange. It is a realm of uncertainty, probability, and particles that behave in ways that seem to defy common sense. Albert Einstein famously called one of its key features spooky action at a distance. It is easy to feel that this is a subject best left to physicists in labs with billion-dollar equipment. But what if it wasn't? What if the keys to this new kingdom of computing could be understood by anyone? What if the journey into this quantum world was not a lecture, but a story waiting to be told, full of wonder and discovery? This is our promise to you. Over the next 20 minutes, we will embark on a journey together. We will start with the mystery you just witnessed and travel all the way to understanding. We will leave the complex mathematics to the textbooks. Instead, we will use clear language and powerful visuals to guide you. We will explore the fundamental ideas, see how these incredible machines are built, and discover the real-world problems they might one day solve. This is not a story about abstract theory. It is a human story. It is about the brilliant minds who dared to ask what if. We will meet the thinkers who laid the groundwork a century ago and the engineers who are today battling the immense challenges of building a working quantum computer. This is a tale of curiosity, of frustrating setbacks, and of breathtaking eureka moments that push the boundaries of science and technology forward. So, get comfortable. Prepare to have your mind expanded. This journey is for everyone, whether you are a tech enthusiast or simply curious about the future. By the end, you will understand not only what a quantum computer is, but why it matters so much. You will see the stakes, the challenges, and the incredible promise. The quantum revolution is not coming. It is already here, and it is time to understand what it means. Our story doesn't begin with computers, it begins with light, and a puzzle that stumped the greatest minds of the 19th century. Their theories predicted that a simple hot object should release an infinite amount of energy, which was obviously not happening. Physics seemed to be broken. In 1900, a German physicist named Max Planck stepped forward with a radical, reluctant idea. He proposed that energy was not continuous, like a smooth ramp. Instead, it came in discrete, tiny packets, quanta. Think of it like a staircase instead of a ramp. This small adjustment solved the ultraviolet catastrophe. But in doing so, Planck opened a Pandora's box. A young patent clerk named Albert Einstein proposed that light itself was made of these packets, photons. Then came Niels Bohr. He described atoms as tiny solar systems. Their debates were legendary. Einstein was troubled by randomness. He said, "God does not play dice with the universe." Little did they know these rules would become the instruction set for a revolutionary technology. For decades, quantum mechanics led to inventions like the laser, the transistor, the very building block of classical computers. The story takes a pivotal turn in the early 1980s with another legendary physicist, Richard Feynman. He encountered a significant problem. Trying to simulate quantum systems on ordinary, classical computers was incredibly difficult. He said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." He essentially proposed turning the problem into the solution. Why not build a computer that operates on quantum principles itself? But it was another thinker, David Deutsch at the University of Oxford, who formalized it into a concrete theory. In a landmark 1985 paper, he introduced the concept of the qubit, the quantum version of the classical bit. Unlike a bit that is either a 0 or a 1, a qubit could exist in a superposition of both 0 and 1 simultaneously. He proved that such a machine could, in principle, solve certain problems much faster than any possible classical computer. The theory was beautiful, but the hardware was nowhere in sight. That was the big gap to close. To understand the power of a quantum computer, we must first meet its most fundamental building block, the qubit. In every digital device you have ever used, information is stored as bits. It is like a light switch. It can be either on or off, a 0 or a 1. A classical bit is like a coin lying flat on a table. A qubit, however, is like a coin spun in the air. While it is spinning, is it heads or tails? The honest answer, a combination of both at the same time. This both at once property is called superposition. It can be a 0, a 1, or a vast continuous range in between. It can be 70%, 1, 30%, 0, 50-50, or any other mix. The moment you measure a qubit, the moment you look, everything changes. The superposition collapses. Quantum uncertainty vanishes. A classical answer emerges. The process: set up qubits in superposition, let them interact in controlled ways, then measure at the end for a final, classical result. Imagine you have a classical computer with 3 bits. These 3 bits can represent only one combination at a time. To check all the possible combinations, the computer has to go through them one by one. Now consider a quantum computer with just 3 qubits, because each qubit is in a superposition. The 3 qubits together are in a superposition of all 8 combinations at the same time. It simultaneously represents 0, 1, 2, 3, 4, 5, 6, and 7, all at once. This property is known as quantum parallelism. This scaling power is exponential. 300 qubits, more combinations than atoms in the known universe. But this power comes with a critical catch. When you measure, you only get one result. It's like 1,000 radio stations playing at once, but your radio can only tune one at the end. Superposition is only one half of the qubit's strange magic. The other half is entanglement. Analogy: imagine a pair of special entangled dice. If you open and see a 6, your friend's die is a 6. Their fates are perfectly correlated. Separate them by miles or by light years. The connection holds. Measure one and it collapses to 0. The other collapses to 0 instantly. But crucially, it doesn't enable faster-than-light communication. Because you cannot control the outcome of your measurement. The final piece of the puzzle is interference. Just like waves of water can combine or cancel each other out. Imagine a giant maze. A quantum computer, using superposition, can explore all the possible paths at the same time. The algorithm manipulates qubits so wrong paths interfere destructively, canceling out. The correct path's waves interfere constructively, reinforcing and growing stronger. This is the true magic. Wrong answers disappear, and the right answer shines brightly, ready for measurement. Shor's algorithm is designed for factoring large numbers, the foundation of much of our modern internet security. A sufficiently large quantum computer could theoretically do it in hours or minutes. Another key example is Grover's algorithm. Imagine you have a massive, unsorted phone book. Grover's algorithm offers a significant speed-up. It's not about making every task faster. Quantum computers are special-purpose machines designed for problems with a specific kind of mathematical structure. When you see a photograph of a quantum computer, you are most likely looking at a superpowered refrigerator, a dilution refrigerator. The quantum states of qubits are incredibly delicate. The slightest thermal vibration can knock them out of superposition and destroy the calculation. To protect them, we must cool the quantum processor to temperatures colder than anything found in nature. Around 15 millikelvin, this golden chandelier is a multi-stage cooling system. Each descending platform gets progressively colder, creating an ultra-cold environment at the very bottom. This is where the quantum processor, the heart of the machine, lives. There are several competing technologies. One of the leading approaches is to use superconducting circuits. Another major approach uses trapped ions. On these chips, the qubits are tiny electrical circuits. The quantum states of this current can be used to represent the states of a qubit. In this method, individual atoms are held in place. Lasers are then aimed with pinpoint precision at each individual ion to manipulate its quantum state. No one yet knows which approach will ultimately win out. We are in the early days of this technology, similar to the 1950s for classical computers. The single greatest challenge can be summed up in one word: decoherence. This is the constant, relentless tendency of a qubit to lose its quantum nature. This fragility is why quantum computers require such extreme isolation. All of this elaborate hardware exists for one primary reason: to fight a constant war against decoherence. Quantum errors are more subtle and insidious. They are small, continuous drifts in the qubit state, gradually pushing it away from the intended path of the algorithm. You cannot simply copy a qubit. Instead, scientists created the logical qubit, use many physical qubits, all entangled together to form one collective logical qubit. If one physical qubit errors, the system can detect it and applies corrective pulses to nudge that qubit back, healing the logical qubit. Quantum error correction is resource intensive. To make one error-corrected logical qubit, we might need 1,000 or more physical qubits. That's why companies build chips with 400 qubits, yet we remain far from running Shor at scale. These are noisy, intermediate-scale devices. The first truly world-changing applications will likely be in the field where Richard Feynman's original idea began, simulating nature itself. Consider the challenge of designing a new drug, designing a new material. To design a catalyst that can efficiently pull carbon dioxide out of the atmosphere is currently impossible. A quantum computer could create a perfect one-to-one digital twin of a target molecule. Scientists could then perform virtual experiments on this digital molecule with perfect accuracy. It could lead to a new era of rational drug design, personalized medicine, revolutionary fertilizers, new materials that could define our future technology. Another major area is in solving complex optimization problems. Think of a delivery company trying to find the most efficient route for its entire fleet. Instead of getting stuck in a good enough valley, a quantum computer has a better chance of finding the single lowest point, the true optimal solution. This could have a profound impact on finance, logistics, manufacturing, energy grid management, and even the training of artificial intelligence models. The immense promise of this technology has now exploded into a high-stakes global race. In 2019, Google claimed to have achieved quantum supremacy. China, in particular, has declared quantum technology a top national priority. The rise of quantum computing is about more than just building the machines themselves. It is about building an entire ecosystem around them. We began our journey in the quiet of a laboratory at midnight. That image, once shrouded in mystery, should now feel more familiar. It represents not magic, but a staggering feat of human ingenuity. The quantum computers of today are like the classical computers of the 1950s. But we know how that story unfolded. This story is far from over. In many ways, it has just begun. New medicines, more efficient batteries, better fertilizers, more powerful AI, all tracing back to quantum calculations. This is a journey that belongs to all of us. Curiosity is the only prerequisite. The world is built on quantum mechanics. It's time we started computing with it. The horizon is brightening. A new day of discovery is about to begin.